In this first video today, we are going to be talking about Lewis structures and just a quick bonding review. So we're going to talk about Lewis structures for ionic compounds and a quick bonding review. So for today, you're definitely going to need a periodic table, and that's pretty much it. All right, so let's jump on in. So we're going to start by talking about ionic compounds. All right, guys, and so ionic compounds are made up of a metal and a nonmetal. So if you remember on our zigzag line, let me draw that up top actually. So on our zigzag line, on our periodic table, everything to the left of that zigzag line is a metal, except for hydrogen. And then everything to the right is a nonmetal. So composed of a metal and a nonmetal. Sometimes you may also see a polyatomic ion in these compounds as well. So not just a metal and a nonmetal, sometimes they also have polyatomic ions in them. What happens in ionic compounds is they transfer their electrons. So our metal transfers its electrons to our nonmetal because metals want to lose electrons, nonmetals want to gain electrons. And they're going to have really large electronegativity differences. So remember, electronegativity is the ability to attract an electron in a bond. And so whenever they form that bond, the attraction of electrons for the nonmetal is so large that it's just going to straight up take the electrons from the metal. Ionic compounds are excellent electrolytes. So electrolytes are aqueous substances that can conduct electricity. Now then, they only conduct electricity when they are molten, so that means liquid, when they are liquid, or aqueous, which is dissolved in water. And to be able to conduct electricity, you have to have charges, and so they're not able to conduct electricity in solid form because the charges are locked in that lattice structure. So there's no way for the flow of electricity to flow through them because those charges are locked in. Ionic compounds have high melting and boiling points. They're generally hard crystalline structures. Their smallest unit is called a formula unit. They form those lattice, like crystal, highly structured structures, and then their naming does not use prefixes. So remember, when you name ionic compounds, there's no prefixes, and to determine the charge, you must swap, drop, and reduce, not to determine the charge, to determine the formula. You must swap, drop, reduce. Okay, so that's ionic. Well, let's talk about covalent now. So covalent compounds are only made up of nonmetals. So nonmetals are to the right of my stair step plus hydrogen. They involve the sharing of electrons. So the electronegativity differences isn't strong enough for any one to steal completely the other one's electrons, so they share them kind of in the middle. And so they're going to have really small electronegativity differences. They cannot conduct electricity, and that's because there's no ions in these covalent compounds to be able to carry the electricity. So again, you have to have those charges. Covalent compounds, they're not charged, they're neutral, so they don't, unable to conduct electricity. They have low melting or boiling points. They're soft solids or gases or liquids. So remember, they are found in all three states, where ionic compounds are most of the time solids. Covalent compounds can be found in all three states. Smallest unit is called a molecule, and there's no order to their structure. So ionic compounds are very ordered, and the way they're done, covalent compounds aren't. And their names do include prefixes, so there is no swap, drop, reduce for covalent compounds. All right, so we're going to start by talking about ionic Lewis structures in this video. All right, so what a Lewis structure is it shows the bonding between atoms of a molecule and also their lone pairs of electrons that may exist on that molecule. So it just shows how bonds happen. So for ionic Lewis structures, they are relatively easy to draw. So let's go ahead and talk about it. So what we're going to do is we are going to draw the Lewis structure for our positive ion with our charge outside of the brackets. If there's more than one positive ion, draw them all with their charge. And then you'll draw your Lewis dot structure for your negative ion, again with charge outside the brackets. And if there's more than one, draw them all. Okay, so let's dive into drawing these structures. And I'm going to show you also where these structures come from. So I'm going to move myself over here. Okay, so I'm also going to show you how these structures come about and then just what your final answer would be. So for our first one here, we have sodium chloride. Okay, first up, we need to come up with our formula. So we have sodium, which is Na, and again, these are all ionic, so we need to swap, drop, reduce. Sodium has a positive 1 charge, and we have chlorine, which is Cl with a negative 1 charge. So we swap, drop, reduce, and we end up with our formula being NaCl. So 1 sodium, 1 chlorine. All right, so first thing I'm going to do to show you guys how we would draw these is just draw our normal Lewis dot structures. So normal Lewis dot structures is our symbol. So in this case for sodium, it's Na, and then the number of valence electrons it has as dots. So sodium has 1 valence electron because it's in group 1, so I'm going to draw 1 dot around it. Now then our other element that we have is chlorine. So again, symbol, chlorine, and the number of valence electrons it has. Chlorine is in group 17, so it has 7 valence electrons. All right, so right here, what's going to happen is chlorine has 7, sodium has 1. All right, so both want to get to 8, so sodium is going to donate its valence electron to chlorine. And then sodium, when it does that, it's left with a positive 1 charge, and it's lost its outer shell of valence electrons, so we just draw it like that. And then chlorine has gained an electron. Ooh, let me space that out a little more. So it's gained sodium's electron. So now chlorine has a negative 1 charge. And this would be our Lewis structure here. That's all we have to draw. Okay. So that's what happens, is that's why we have those structures and those positives and negatives. It's because of that transfer of electrons. So now we're just going to look at how to draw them without those. Okay. So moving on to our next one, which is magnesium fluoride. All right. So step 1, determine our formula. So magnesium is Mg, and magnesium has a positive 2 charge. And then fluorine is F, and fluorine has a negative 1 charge. So swap, drop, reduce, and we end up with MgF2. Okay, so now we're going to use these charges right here that we just determined to draw our things. All right, so magnesium has a positive 2 charge, so that means it's lost 2 electrons. Magnesium only has 2 valence electrons, so it's lost all of its valence electrons. So it's going to be Mg with a positive 2. Well, then fluorine has negative 1 charge, so it's gained 1 electron. So fluorine, then, since it's gained 1 electron, it had 7 valence electrons. It's gained 1, so it now has 8. It's going to be F negative 1. So those are my Lewis structures for each of my 2 ions here. The only thing I need to note is that I do have 2 fluorines, so I do need to draw 1 more fluorine in my compound. And I generally, when I draw them, I do generally try to make sure that my metal and my non-metal are next to each other, just because that's most of the time how it's drawn. And how it would actually bond is that our charges would alternate between positive and negative. You wouldn't have like 2 negatives next to each other because they don't attract. Okay, let's do a couple more together. All right, so this next one is rubidium oxide. So we have rubidium, which is Rb, oops, that's a P, Rb, and rubidium has a positive 1 charge. And then we have oxide, which is O, the negative 2 charge. So we swap, drop, reduce, and we end up with our formula as Rb2. I can write O. Okay. So we have rubidium has 1 valence electron, but it's Rb plus 1, so that means it's lost 1 valence electron. So it's going to be Rb, it's lost its only valence electron. So, well, now it's down to the next row, but it's lost its outer shell. So it's going to be Rb with a plus 1. Then we have O negative 2. So oxygen normally has 6 valence electrons. We have that negative 2 though. means we've gained 2 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8 now. So it had 6 originally. So oxygen with a -2. 2 rubidiums, so we need to draw it twice. Boom. Let's do one more, and then I'm going to leave you guys to do the last 2 on your own as practice. Okay? So calcium sulfide. So we have calcium, which is Ca, +2 charge, sulfide, F with a -2 charge, swap, drop, reduce. We end up with CaS. Okay, so calcium. Again, just using my charges from right here. Calcium has a +2 charge. Calcium has 2 valence electrons, but it has lost those 2 valence electrons. So it's going to be calcium +2. Then we have sulfur. Sulfur has 6 valence electrons, but it has a -2 charge, so it's gained 2 electrons. So sulfur is going to have 8 valence electrons around it and have a -2 charge. Okay, so you guys go ahead, pause the video, and try to work out the last 2 problems on your own, and then restart the video and we'll go over them. Okay, so pause your video now. Over them. So right here we have sodium nitride. So sodium is Na with a +1. Nitrogen is N with a -3. Swap, drop, reduce, and we end up with Na3N. All right, so sodium has a +1 charge. So that means it's lost 1 valence electron. Sodium normally has 1, so since it's lost it, it just becomes sodium with a positive. And then nitrogen normally has 5, it's a -3, so it's gained 3 electrons. So it's going to be nitrogen -3 there, those 3 electrons from the sodium. So this is what I drew our Lewis structure as. And again, I just spread it out so that the nitrogens were on different sides because those positives and negatives don't attract. And then our last one is lithium fluoride. Lithium is +1, fluorine is -1. Swap, drop, reduce, we get LiF. Lithium has that +1 charge, so it's lost that 1 electron. Fluorine has a -1, so it's gained that electron. And that's what our Lewis structure would look like. Okay, guys, that's it for Lewis structures. There will be practice posted on Canvas, so make sure you complete that so that you know what you're doing. All right, bye.